Why does light bend when it enters glass? If you ask most physics students, they'll tell you it's because light slows down. Take a look at this diagram. On the left, light hits the glass at an angle and bends. But on the right, light travels straight along the normal line. It still slows down, but it doesn't bend at all. So a drop in speed alone cannot be the full explanation. To secure full marks on an exam, we have to abandon the one-dimensional ray model. We need to visualize light as a series of parallel wavefronts, much like ripples on the surface of water. By examining the two-dimensional width of these wavefronts, we can uncover the true mechanical cause of the bending. Glass is more optically dense than air. That optical density is the specific environmental condition that restricts the light's speed. In this zoomed-in view of the boundary, notice the precise moment of contact. Because of the approach angle, the bottom edge of the wavefront hits the optically dense glass first. It immediately slows down, but the top edge is still traveling through the air at its original, faster speed. With one side moving slowly and the other side still moving fast, the entire wavefront is forced to pivot toward the normal line. Refraction is never caused by an overall drop in speed. It is caused exclusively by the differential speed across a single wavefront as it enters a new medium. We can see this mechanic in an everyday physical analogy. Driving a lawnmower from smooth pavement into thick grass at an angle. The right wheel hits the grass first and gets bogged down. The left wheel remains on the fast pavement, and that imbalance forces the machine to pivot. These mechanics map directly back to the physics. The mower's wheels are the edges of the wavefront, and the thick grass is the optically dense glass. Now it's your turn to test your understanding. Pause the video and write down a 3-step explanation for refraction. To simulate real exam conditions, your written answer must explicitly use the terms wavefront and optically dense. Actively retrieving this specific vocabulary right now forces your brain to lock in the memory, which prevents simple point deductions on test day. Welcome back. Let's look at the definitive exam-ready answer. Mark 1. One part of the wavefront reaches the more optically dense glass and slows down first. Mark 2. The other part is still moving faster in the air. Mark 3. This differential speed causes the wave to bend towards the normal line. If you revert to the intuitive idea that light bends simply because it slows down, you will score 0 marks. The rubric demands the mechanical detail of the boundary interaction. Screenshot this summary. By saving this, you now possess the exact mechanism, the required vocabulary, and the physical analogy required to conquer this topic.